So for section 3.1, we're going to be prepping linear equations with two variables. Most of our equations we're going to see in this section are going to be in standard form. That's where we have ax plus by equals c, where a, b, and c are going to be numbers. And with any equation like this, we're going to get a solution. The problem is, depending on x, we get lots of different y's, right? Or depending on y, we get lots of different x's. This is why in our previous problems when we would solve, a lot of times we would get different answers if we plug in different numbers. Well, we're prepping ourselves to get to graphing. It's basically a way of illustrating all of the different solutions there are to this equation, ax plus by equals c, if a and b and c are numbers. That solution will be an x and a y, and basically that is a point or what's called an ordered pair. So here's an example of a linear equation, 2x plus 3y equals 12, and they say, is 3, 2 a solution? Well, you have to go, okay, every point is listed as x comma y. That's our solution, x comma y. And so what I do is I take that 3 and I put it in place of the x. I take that 2 and I put it in place of the y. And so we substitute both in to see if that is the solution. So we get 2 times x, 2 times 3, plus 3 times y. And if it's true, it should equal 12. So we get 6 plus 6 equals 12, or 12 equals 12, which is true. And if it is true, then we say yes, it is a solution. Is negative 2, 7 a solution? We're going to do the same thing. So this time again, that first number is our x. So that first number is going to be plugged in for the x. The second number, the negative 7, is our y. So we'll plug that in for y. So be careful, and I like the parentheses here because if you just put a little dot, here's where people are going to have an issue. It's not 2 minus 2, right? It's not 2. One thing that scares me is I'll have some people go, well, up here, like they'll put 2, 3, and they'll call, oh, it's 23. No. This means 2 times x, so it's 2 times that negative 2 plus 3 times the y, negative 7, equals 12. So let's say 2 times negative 2 is, it's like negative 4, plus negative 21. I don't think it's going to work this time, because negative 4 plus negative 21, negative 25 does not equal 12. Or 2. Does not equal 12. So if it's not true, then we say it is not a solution. So there will be some points that are true. Well, was there only one solution to this ever, right? Well, let's see. Let's try another one. 2 times this negative 6x, 2 times negative 6, plus 3 times the y of 8 should be 12. Is negative 12 plus 24 12? 12 equals 12. That is true. So it is a solution. This point is a solution. It is one of the possible combinations of x and y, one of the possible combinations that would give us the number 12. Find y. Okay, I thought I erased all these, but here we got x. Here we're finding what is y. What if x were 0? Could you find what y is? Well, 2 times the x we know, plus 3 times y equals 12. 2 times 0 is 0 plus anything. And you have to remember from before, how do I undo this 3? Do not subtract 3. That should not be happening at this point, right? Undo the multiplication by using division and get that y equals 4. So our point of solution is 0, 4. You could check this. I could do 2 times x, 2 times 0, plus 3 times the y we got, and say 0 plus 12 equals 12, 12 equals 12. Hooray. This is the y value. What if they give me a y value? The y value this time is 5. Well, we can plug that in for y, and we can solve for the missing x. So, 2 times x we don't know, plus 3 times y this time is 2x plus 15 equals 12. I undo the addition with some subtraction. Have a calculator by now. You should not be doing this without that technology, especially if you're struggling with the integers 12 minus 15. And was that a 2x? It was a 2x, wasn't it? So dividing by the 2, x is negative 3 halves. There must be something wrong, right? You're like, it's a fraction. That's never possible. Let's check. 2 times x plus 3 times y should equal the 12. 2 times 3 halves, I'm going to make that 2 over 1. In fact, I'm going to just kind of cancel the 2's. That's what I would do. You could make that negative 6 divided by 2 is still just negative 3 plus 15. And so I get 12 equals 12. That means that negative 3 halves was right. You need to know how to use this because we're going to be using this to complete tables and eventually get to the point where we can graph and see these solutions visually. So here I have x minus 2y equals 8. Not a pretty equation. We'll actually know how to clean those up later. But I've given you some x values and I'd like you to find the y values. So if x were 2, we would have 2 minus 2y equals 8. Subtracting the 2, negative 2y equals 6 this time. Dividing, y is equal to 6 divided by negative 2. That would go here. We plugged in the x, and we got the y this time, right? Well, the next one, we're doing the same thing. We're plugging in an x, so 10. Subtract. Negative 2y is equal to, how about negative 2? We undo the multiplying, not by adding, right? We undo multiplying by dividing by the same number and get that y is equal to positive 1. Well, we got 2 more, but this time I'm not given the x, this time I'm given the y. So what if y was 0? Well, x minus 2 times 0, not 20, equals 8. 2 times 0 is just 0. X equals, well, that wasn't too bad. What if y was negative, or what if, y was negative 2? X minus 2 times a negative times a negative. Moving that over, x equals 4. All of these are points. All of these are solutions for this. We got 2, negative 3. We've got 10, 1. We've got 8, 0. And we've got 4, negative 2. Why do they call this a linear equation? Well, if I were to plot these points, 2, negative 3, 10, 3, 4, 5, 6, 7, 8, 9, 10, 10, 1, so up, my line stinks anyway, so 10, 1, okay, 8, 0, and I got 4, 1, 2, 3, 4, negative 2. If I plot all of these points, they should form a straight line. In fact, if they don't, like I almost put a wrong dot there, right? Then we know that one of those points would have been off or would have been wrong, would have been a mistake, okay? These are called linear equations because literally when I plot all of the points that make their solution, they form a straight line. Okay, now this is another interesting equation, x equals 5. How would I make a table for this? Well, I've already done the first one for us because I want you to see. If x is 5, would y be 0? Plug that 0 in for y. There is no y, right? If y is 0, x is still 5. What if y is 6? There's no y to plug into. X is still. So basically, when you have x equal to a number like this, y can equal as long as x equals 5. I could have 5, 0, 5, 1, 5, 2, 5, 3, 5, negative 1. Is this still a linear equation? Well, let's see. 1, 2, 3, 4, 5, 0. We said 5, 1, 2, 3, 4, 5, 6. Why did I pick something so high? 5 anything, right? 5, 1, 5, negative 1. Is this still a line? This is a vertical line. X equals 5. We can graph by filling in the table and plotting points and knowing that it ends up becoming a vertical line. What if I got y equals 4? Well, this is similar to the last one, because if y is 4, what could x equal? Well, it could equal 0, couldn't it? If I try to stick that 0 in place of an x, there is no x. So we get 0, 4 as one of our points. What if x were 2? Y would still be? What if x were, this time, x can be? Because there is no x that changes the equation. There is no x in the equation. So we end up with, it could be 1, 4, it could be negative 1, 4, it could be, x could be anything. So let's see, 0, 1, 2, 3, 4, 2, 4. Did I mess up on something? Yeah, okay, about to get myself in trouble. If x is 2, 4, anything 4, including 1, 4, negative 1, 4, we still end up with a line that is what? That's why these are called linear equations, because if I go graph all the solutions, that would be a straight line. Let's plot some points. Okay? So we just kind of went through that a little willy-nilly. I want to see, we're going to actually focus specifically on plotting points. Take a second, draw your XY axis, okay? Most important thing right off the bat is to know which axis is X and which one is Y. Which one comes first? And so what I like to do is I like to say, okay, well, if you went through, and I had some experience in elementary education, and you look at these number lines that they had in all these elementary classrooms, what did they look like? Well, they were this number line going across the ceiling, right? All the way left and right, and that was our x-axis. You didn't even know it, but that was the x-axis. That's our first number line we dealt with. We're going to the right, x is positive, and going to the left, x is negative. And we were fine with that in mathematics for many years. We just kept the x-axis going left and right. But then a mathematician named Descartes said, I think there's more we can do with this. So we took, and he added a second axis. And since the first one was x, the next letter that followed was y. And going up, y is positive, and going down, y is negative. And then now that we have both of these axes, by the way, I know that the mathematician Descartes did it, and I think this kind of thing is interesting, which is why they call these the Cartesian coordinates. Points are also known as Cartesian coordinates. Why? Because the guy's name was Descartes, and since he invented it, he named it after himself. So if you invent something in mathematics, you get to name it after yourself, and then people get to forget about it and not care anymore. All right, so negative 3, 2. We already said each of these is an x and a y. What the positive and negative do is they give me direction. See, x is positive when it goes to the right. The x values are going to go either right when they're positive or left when they're negative. The y values are going to tell me how far to go, up when it's positive or down when it's negative. So let's see, this was the x-axis. This is the y-axis. Going to the right and up, all the points that are in here. All of the x values are to the right, so they are positive. Going up, all of the y values are positive. Every point in this region, the x values and y values are going to be positive. If the x value is negative, then instead of going to the right, we will go to the left. That would be like up here, where the x values are negative because we went left, and the y values are positive because we go up. Left and down, x values are negative, y values are negative. Left and down. If I go right and down, x values are now right, so positive, and y values are down, so negative. This splits the xy axis into 4 regions. We call those quartiles. Quarter 1, probably not quartiles, that's statistics. Quarter 1, 2, 3, and 4. Quadrant, there's the word. Geez, I'll write that down. Quadrant, my brain. Quadrant. So 4 quadrants, 4 regions. Quadrant 1, 2, 3, and 4. Okay? So what we're going to do is we're going to plot these, and then we're going to find out what quadrant they're in. Well, I see a negative and a positive. I'm already predicting quadrant 2. But what we do is this negative 3 says go 3 to the left and 2 up. From where? From the beginning. This point in the middle has a name as well. One more word to fit in here. This is called the origin. That's where we begin. If you think about what does origin mean, if we talk about the origin of mankind, we're talking about the mankind's beginning. So that's called the origin. 0, 0 is where we begin. And from there, I will go 3 to the left and 2 up. And that is point A. And it is in quadrant 2. 5, negative 1 is right and down. I'm thinking quadrant 4. Verify. From the origin, I start back at the beginning. I'm going to go 5 to the positive and 1 negative down. So from the origin, 1, 2, 3, 4, 5, and down 1. That would be point B. And it was in quadrant 4. 4, 6, they're both positive. Both positive happens in quadrant 1. 4 here positive means 4 to the right since it's our x, and 6 positive, 6 up. So 1, 2, 3, 4, and up 1, 2, 3, 4, 5, 6. Sorry about that. So hopefully, I'm sure you can all just scoot stuff over too. And that would be point C in quadrant 1. My 1 stinks. All right, just put 1. Don't get all fancy. Negative 3, negative 4 is both negative, so I'm thinking quadrant 3. Negative 3 is 3 to the left and 4 down. 1, 2, 3. 1, 2, 3, 4. That would be point D. 0, negative 3. Now that's hard to predict because I see this negative, but the other one's 0. What does that 0 mean? How far am I going right or left? 0. Don't move. It just says don't move, basically from the origin. Don't go left or right, but only go 3 down. So I stay at the origin and I go 3 down. And that would be point E. But it's what quadrant's it in? Well, it's between 3 and 4. So you know, between 3 and 4. No. There's a name for that. It is on this line between 3 and 4 called the y-axis. In fact, any point on the y-axis will have an x value. I should probably add that on there. An x value equal to 0. Any point with an x value of 0 will be on the y-axis. Well, here's a negative 6, 0. That says go 6 to the left, and what's the 0 mean? Don't move. From the origin, go 1, 2, 3, 4, 5, 6 to the left, and don't move. Plot the point right there. That's F. Where's that on? Well, it's between the two quadrants. It's on the line, which is called the x-axis. Notice this has a 0 this time for y. Anything on the x-axis will have a y value of 0. And last but not least is 0, 0, 0, 0. Says just don't move at all. That would be G. And that is on the origin. We're almost done. You're going to have some questions where they give you a bar graph or a line graph. Two ways of displaying kind of the same data. So let's say in 2004 there was, I don't know, we'll say a profit of $6,000. Not a great business. But the next year it went up to about 65, and that finally gets to 7,000 in 07. So where's 07 up there? It gets to 7,000. Okay. So what we can do is you can actually kind of see what these are, because you take each of these bars and you bring them to the left, and we can approximate what each of these bars is worth. So if I take their height and I bring it over, then I can say, well, in 2004 we had a profit of 6,000. The next year, a little bit about halfway, maybe 6,500. The next one, closer to that, so maybe 6,800. And the last year goes all the way up to 7,000. I can do that with a bar graph for categories, or I could do that for years. And I just plot them out as a line graph as the dots move up and down. Once again, the 6,000 is here. Bring this next one over, bring this next one over. So it's the same thing. I can bring these over. I have 2008. Looks like that's about 7,500. So you can take, if they ask you to read them, you take the y value, you bring it over.